care about, and that's the money. Hello, guys.
Hello.
Good morning.
Good morning, everybody. Okay, it's 9:59. Shall we start early? Finish early? Okay. Yeah, let's go ahead and get started with this. And then you can go on to other important facets, other classes. I know some of you have jobs and so on, so we'll get through this. All right, now, so you're all becoming experts in StatCrunch. When you finish this course, you'll have something of real value, I think, under your belts. And that is a knowledge of elementary statistics and how to calculate those statistics using the spreadsheet. So that's what you're going to gain from this semester. Okay. And who knows, in a future course, you may have to collect data, real data, and analyze it. And you'll know how to do that, at least at the elementary level. And that goes a long ways, believe me. All right, then, so let's get started here with this week's worksheet.
Stars,
Yes.
I have a question. Not anything to do with the worksheet, but when's midterms?
The midterm is a week from Thursday, October the 22nd. I had announced that date some time ago.
Cool. Thanks. Sorry, I've been looking for it and I couldn't find it.
Okay. Yeah, I'll post the date again in an announcement. All right. Just to remind you that it's coming up. We won't have a session this Thursday. So our next session will be a week from today. We'll go over the worksheet that I'll assign, and then we'll spend some time in review for your midterm. And I'll set out the ground rules for the midterm and define the scope of the midterm. Over what chapters will it cover? All right, so that's the midterm. Thursday, this coming Thursday is the 15th. Today is the 13th. So this coming Thursday is the 15th. And your midterm exam is a week from this Thursday, which will be October 22nd. All right, and your final exam is the last day of the course. And for us, I believe the last day of our course is going to be the 12th. Okay. So wait, let's see. The last day of our course is Monday the 14th. All right. So I'll give you the final exam probably that Monday with a day or two to turn it in. Okay. So midterm October 22nd, a week from this coming Thursday. And then the final exam is December the 14th. Okay. which is a Monday. Curious that the semester falls, the end of the semester falls on a Monday, but that's what it is this semester. Any other questions before we get started with the worksheet? Okay. I'm still admitting students, so let's go ahead and get this started. I'm looking at the chats here, and one student wrote, "R.I.P. Padres." Well, as you know, the Padres made a lot of progress this year. It's just a 60-game season, but it looks promising now for the next few years to come. So hopefully they won't disappoint us. I didn't feel disappointed, but without pitching, starting pitching, the baseball fans out there know that in the playoffs, it's all about pitching. It doesn't matter if you have 9 Tatis, you still need a couple of pitchers. And we didn't have that, did we? All right, guys, let's get started. Okay, I have a chat here from Noah, and maybe we can go over that later. I don't quite understand what he's telling us there, but anyway. Okay, so let's get started with this. And for this one, I have posted some videos for you to watch, which explain how to do the calculations in StatCrunch. So what we'll go through here today are the StatCrunch results. And after viewing these videos, you should be good to go. They're short videos. I don't think any of them are over 10 minutes. And as you do your calculations in StatCrunch, you can use these videos to help you, all right? Okay, so in the second problem, it says here, the average amount of time boys and girls aged 7 to 11 spend playing sports each day is believed to be the same. A study is done and data are collected, resulting in the data in the table. Now, one of the underlying assumptions is that the populations from which you're sampling are normal. Okay, so that gives us a way to justify the use of the test statistic, which may have a normal distribution if all the assumptions are met. One of the assumptions is that the underlying populations from which you're sampling are normal. Okay. This is a 2-sample problem, and analysis of variance, or ANOVA, is a topic that we'll cover later. And that is a similar problem where you're testing different means across more than 2 populations. So I want to plant that idea in your head now that in elementary statistics, you can actually consider more than 2 samples. Here we're considering 2 samples and comparing the means across the 2 samples. So a comparison across means of several samples is known as the analysis of variance. Okay, we'll come to that later at the end of the course. So here's the summary data where we're given the sample sizes of each sample. Girls 9, boys 16, the average number of hours. So the sample mean for the girls is 2 hours, and the sample mean for the boys is 3.2 hours. And then out here in the last column of your table, you're given the 2 standard deviations. Okay, again, these are in hours. Now up here, we want to test the claim that the number of hours is the same. Okay, that's not obvious from the summary data. So the sample means are different, aren't they? But because of the incongruency of sampling, we know that noise can enter a sample, and the standard deviation is what gives us a clue as to how the variation will play its role. So the next thing we need to do is write out in complete English sentences what the claim is. So what we're trying to do is simply establish that there is a difference in means. Remember, we're testing the population means now based on the sample means. And our notation for the population means is mu1, mu2. Okay. We'll deem population 1 to be the boys, population 2 to be the girls. And so the statement of the claim, or what we also call the null hypothesis in hypothesis testing, is there is a difference in means mu1, mu2 of the amount of time boys and girls aged 7 to 11 spend playing sports each day. Okay. Now, hypothesis testing has a setup where we establish the null hypothesis and we establish what's known as the alternative. And typically, the alternative hypothesis embodies the claim. The claim is that there's a difference. Okay. So we'll always set up the null hypothesis to be there is no difference in means. That is, the difference is 0. Against the alternative that there is a difference. We're not saying that it's greater. mu1 is greater than mu2. We're not saying that mu1 is less than mu2. In this particular instance, all we're saying is that they're different, that they're not equal. In that alternative scenario, we have what's known as a two-tailed test, where we reject the null if the difference is too large or if it's too small. In the other two cases, we have what's called one-tailed tests. Either the right tail, in case the alternative is mu1 greater than mu2, or else the left tail, mu1 is less than mu2. Okay? So that's the formal way that elementary statistics sets up the hypothesis test between two means. Now, in your video, you'll see how to calculate these statistics in StatCrunch. So you need to go into your video and pay attention carefully to the instructions And you'll go ahead and set up your z-test or your t-test. T is also used in calculating your test statistic based on if the sample sizes are small, based on if the standard deviations are not given, that is, the sigmas are not given, but you're estimating the sigmas using the S's, the sample standard deviation. That's usually the case in reality. But if the sample size is large enough, typically if both samples are greater than 30, you can use the Z distribution as long as you're sampling from normal distributions. Okay. All right. So that's a little bit of the theory of sampling and testing for two means. Okay. This is the output that you'll get from your test in StatCrunch. All right. You'll give it the summary data, which is the sample size of the first sample, the sample mean of the first sample, and the sample standard deviation of the first sample. You'll also give it the summary data for the second sample. You'll set the significance level, remember confidence level? Okay, this is similar. The significance level of the test is known as alpha. 1 minus alpha is the confidence level. So if alpha is 5%, if the significance level is 5%, the confidence level is 95%. So those critical values determine the rejection region. Okay? So let's see what happened here in this data. Here we have small samples. So we're in the T regime, as I just mentioned. Okay. Both samples are less than 30. We've estimated the sigmas using S. All right. But most importantly, we're sampling from a normal distribution in both cases. Okay, so that allows us to use the T. Okay, and here we have the degrees of freedom of the T. StatCrunch will calculate that for you. In your textbook, you'll see a formula for the degrees of freedom as N1 plus N2 minus 2. Okay. All right. Sorry, N1 plus N2 minus 1. Let me do that again. Yes. I said it right the first time. N1 plus N2 minus 2. Sorry for the mistake there. Okay, and here it is, 23. All right. Okay. Remember, with a T distribution, you have to take into account the degrees of freedom. Right? Now, what is our test stat? Our test stat is based on a score. We talked about z-scores. And let me see if I can convince you that the score is a measure of how far away the test statistic is from the mean. Remember the heights of the two tallest people in the world. We compared their z-scores. The z-score was the value x, in this case, x is the difference of the sample means, minus the population means in the null hypothesis, the population means are equal. In other words, their difference is 0. And then we divide by the standard error of the estimator, which in this case is x1 bar minus x2 bar, right? All those formulas are given to you in the textbook. Okay? I just want you to understand that the test statistic is a score. It determines how far away the difference in means is from the difference in population means, which is assumed to be 0. Okay? If that test statistic is too large or too small, we'll reject the null hypothesis. Okay? The assumption that the means are equal tells us that the difference is 0, and if we're too far away from 0 in the score, then we'll fall in one of those rejection tails. Okay. And then there's an alternative score that we use called the p-value, which is simply the probability of the test statistic falling outside of the value 0, right? Okay. All right. So in this StatCrunch output, you see the t-stat, which is above 3. Now you know that in z and t, 3 is far away from the center of the distribution. It's more than 3 standard errors from the distribution. So that should raise a flag there. It's pretty big. 3 is pretty big. Remember, with the normal distribution, 99% of the data is within 3 standard deviations. So if you're beyond 3 standard deviations, that raises a flag, and you'll probably reject the null hypothesis. Okay? All right. And then this p-value is a measure based on the probability that you're greater than the test statistic. And notice that probability value here, p-value, is quite low. And when we compare it to the significance level, alpha, which is 5% in this case, it's much smaller than alpha. If the p-value is low, the null hypothesis is a no-go. Okay? If the p-value is high, typically bigger, greater than alpha, then the null hypothesis will fly. We will not reject it. Okay? And here is a drawing of the rejection region. Now, how did we generate this drawing? We went to the t-calculator for 23 degrees of freedom, and we set the tail probabilities equal to alpha over 2. We have to have a total of alpha. The distribution is symmetric, so we have to have alpha over 2 in each of the 2 tails. This is called a two-tail test, because the alternative hypothesis is that mu is not equal. Mu1 is not equal to mu2. Not greater than, not less than, but different than, not equal to. So this is called a two-tail test. And the rejection region consists of 2 tails, the left and the right. All right, and so that's exactly what this picture is telling us here. So the rejection region spans on the t-axis between -2.0687 all the way up to 2.0687. 0.0687. Okay, so if your test statistic falls outside that range, then we're going to reject. Okay, so I'm giving you a little bit of the theory and application of the hypothesis test here. How do we state the conclusion? This is very important. I have a lot of students who get bits and pieces of the conclusion correct. Okay. Now remember what our alternative hypothesis was. That was the claim that the number of hours is different. Okay. So how do we state the conclusion properly? Pay attention here because this is important. You can lose points if you don't state the conclusion correctly. Now, what we have here is a sample of data that doesn't give us evidence that the null hypothesis is correct. On the contrary, it tells us that the null hypothesis is incorrect. But it's just one set of data. So what we have to do is preface our conclusion by saying that at the 5% level of significance from the sample data, there is sufficient evidence to conclude that the means are different. Okay. Now I've added in quite a few words here, but the important parts are at a particular level of significance. The data, the sample data, that's all we've got, does provide sufficient evidence to conclude that there is a difference in the amount of time girls and boys play sports, okay? So that's the conclusion, all right? And again, as we go through each of these problems, you'll see how to state the conclusion properly. In this particular example, we've rejected the null. That's not always the case. In certain examples, we won't reject the null, will we? Based on the sample data. Okay. Any questions about number 2? Now, one important piece of the puzzle here is that I haven't shown you how to do this in StatCrunch. Okay, so you'll have to go to your video if you haven't already looked at it, and you'll see how to do that. It's fairly straightforward. Okay. And again, here, question?
Yeah. On our worksheet, it asks like what the value of A is for that problem.
What the value of what?
A is.
Where does it ask that?
On the actual worksheet itself, fill in the table completely with justification. As H of O, H of 1, state whether the test is two-tailed, left-tailed, or right-tailed, and the value of A equals.
All right, so let's see. Well, this is the assignment that I gave you. Oh, you're looking here. Okay, this solution set that I'm showing you does not have these boxes, does it?
No.
Okay. but it has all of the values that these boxes are asking you to fill in, right?
Yeah.
Okay. So, you know, you have some flexibility in preparing your worksheet. So you can follow this format here, okay? And this part C here doesn't make any sense, does it, for this problem? That shouldn't be there. Okay. Now, with what I went over with you here in this first problem, would you be able to fill in each of these boxes? What is your null hypothesis here? H sub 0.
I'm not sure.
Okay. Well, in notation we would say the population mean mu1. Don't have to write out all this, but you would just say mu1 is equal to mu2 versus the alternative H1, mu1 is not equal to mu2. As I stated, it's a two-tailed test because you're looking at the inequality in the alternative mu1 not equal to mu2. If it were mu1 greater than mu2, it would be right-tailed. Otherwise, it's left-tailed, mu1 less than mu2. What's alpha here? Alpha is our significance level, and it's given to be 5%. And the formula for the appropriate test statistic, as I told you, is simply the difference in means minus the difference in population means divided out by the standard error. And the standard error is given to you as a formula in your textbook, okay? All right, so that's the test statistic. And the value of the p-value, the value of the p-value is given to you from StatCrunch. I told you what the critical values were based on a t-distribution with 23 degrees of freedom. And we did go over the statement of the solution. Okay. All right, so as you go through those boxes, you'll be able to answer all of those boxes based on your results in StatCrunch. And what I did want to emphasize here is that you will have to submit your companion StatCrunch file, your .scs file with all of your results here, okay? So here is the null hypothesis, okay? This is copied and pasted right out of StatCrunch into your worksheet. Here are the test results from StatCrunch. And here are the basis on which the decision to reject or not reject is made. These are the two methods, either using a critical value method by defining the rejection region for the test using the test statistic, or by simply comparing the probability value, okay, with the significance level alpha, which is 5% here. Okay. Right.
So just to make sure, I think I heard you say that we don't have to do part C on the worksheet.
That's correct. That's a typo.
Okay.
Okay. Some of you may use that format that I gave to you in your worksheet. Others will just copy and paste your results right from StatCrunch into your worksheet. Some of you have already done that, done it that way. Okay, let's come to the second problem now, where we have two classes, one that's been taught online, the other has been taught face-to-face. So let's read the problem here. A professor at a large community college wanted to determine whether there is a difference in the means of final exam scores between students who took his statistics course online and the students who took his face-to-face statistics class. He believed that the mean of the final exam scores for the online class would be lower than that of the face-to-face class. Right now in virtual environments in education, there's a big controversy over how effective is online teaching. So here's one professor, and here's his data, and he claims that he believed that the mean of the final exam scores for the online class would be lower than the face-to-face class, okay? So was the professor correct? And here is the data that he collected. He randomly selected 30 final exam scores from each group, and he's listing the data here. Okay. The first data set is his online class, and the second data set is the face-to-face class. And there you see all the data. You know, the test scores range from 0 to 100. Okay. So what we're going to test is the following. Is the mean of the final exam scores of the online class lower? Is the mean, mu1, let's call it, of the final exam scores of the online class lower than the mean of the final exam scores of the face-to-face class? We'll use alpha equal to 5%. Okay. And we'll answer the following question. Following questions. Is this the test of two means or two proportions? Well, he's testing online versus face-to-face, so it's a test of two different means. Are the population standard deviations sigma 1 and sigma 2 known or unknown? Well, the sigmas are not given to us, are they? Remember, I mentioned before that typically they're not given. So we'll estimate them using the sample standard deviations. So the population standard deviations are unknown, and we'll use pooled variances. So our assumption is that the variances are the same for both populations, which will allow us to pool the variances. If you don't make that assumption, then StatCrunch gives you a way to test using different variances. But we're not told that the variances are different. So we'll assume that we can pool the variances across the two populations and use that variance, okay? The difference in sample means is our test statistic. Okay. We'll denote X1 bar to be the sample mean of the online scores, and X2 bar is a sample mean of the face-to-face scores. Okay. What are the null and the alternative hypotheses? Well, remember, the null is that they're the same, but what is the alternative? The alternative is, in fact, that the online scores are lower. So he's testing mu1 less than mu2. That puts him in the left-tailed test region, okay? Because that inequality is less than. Now remember that mu1 is the population mean for the online course, right? So if his claim is that the online courses on average are lower, then he's stating that mu1 is less than mu2. Okay. All right. Or that the difference mu1 minus mu2 is less than 0. Those are two equivalent statements. All right, let's see what the data tell us now. Can the data support his claim? That is, will the data allow us to reject the null hypothesis in favor of the conclusion that the online scores are lower on average? Okay. Now, using StatCrunch here, we get the following results. Let's first take a look at the sample sizes. The sample sizes are both 30. We can use the t-test, okay? Remember, z is used when both sample sizes typically are greater than 30. This falls right on the margin, all right? And so to be safe here, or to be conservative, we'll use the t-test. What are the sample means? All right. Now in StatCrunch, you don't have, I'm sorry, up here in the problem, you don't have the sample means, do you? So how do you calculate the sample means? Okay. Let's see. Who do we have here?
I can answer.
Yeah. What is your name?
Trevor. So are we going to have to type all those statistics into StatCrunch and then use the summary stat?
Yes. Okay. You could use your statistical calculator. You could use your basic definition of just adding up the data and dividing by 30, but you hit the jackpot, Trevor. What you want to do is take your data, populate your spreadsheet in StatCrunch with the data. We've done that several times before. And then you can go to Summary Stats, calculate your sample mean and your standard deviation. Do that for each of the 30 values here. Okay? All right. It's not as tedious as it looks. I would say that in under 5 minutes, you could type in all of these different values into your StatCrunch spreadsheet. Okay. Now, that gives you lots of benefits, doesn't it? It allows you to calculate the summary stats. Your data typically will be typed into your spreadsheet in a column. You'll have one column for online test scores. You'll have a separate column for your face-to-face test scores. And you'll calculate the summary statistics of each of those columns in summary stats. We've done that before. And it'll give you the summary statistics. Turns out that the face-to-face mean, sample mean, for those 30 values is higher. But is it significantly higher? Well, that depends on the standard deviation. Okay? So let's calculate our test statistic here. And look, it's pretty high, isn't it? And in supporting that conclusion, we see that the p-value is very small. Remember, if the p-value is low, the null hypothesis is a no-go. If the p-value is high, the null hypothesis will fly. Just remember that little ditty in your head. But also, the t-statistic is large, isn't it? Remember, t-scores typically above 3 tell us that null hypothesis that the means are the same is not correct. Okay, the mean difference is probably greater than 0, not 0. Okay, so based on these results that we get out of StatCrunch, we can say that at the 5% level of significance from the sample data, there is sufficient evidence to conclude that online scores are lower than the face-to-face scores, right? There's a negative in here, right? In the t-stat, the negative sign should be in front of this value, but that just tells us that it falls in the left tail, okay? Remember what our test statistic was. It was subtract x1 bar from x2 bar. X1 bar is 72.85 and x2 bar is 84.98. So that's a difference of more than 12 points, right? And in terms of a t-score or a t-stat, that gives us a negative 3.22. All right, 3.23 if we round to 2 places. Any questions about number 2? There's a lot going on there, isn't there? Decide on whether to use T or Z. And typically, if the sample size is less than or equal to 30, we would use a T. In addition, we're estimating the population standard deviations from the sample standard deviations. That's a requirement to use the T. Okay. Furthermore, our t-score is very high or very low, in this case, very low. It's on the left side of the rejection region, has a probability value of less than 0.001. And in addition, I don't show the critical values here like I did in number 1, like in number 2, right? But the critical values are going to be probably around 2, like they were in number 2. Okay, so there's a lot going on here. And how do you solve the puzzle? Okay. type in your data right into StatCrunch, calculate your summary statistics, use that summary in your 2-sample t-test, and you're off and running. Okay, let's go to the last problem here. Oh wait, number 4. Where are we in time? We're doing good on time. Okay, so an interested citizen wanted to know if Democratic US senators are older than Republican US senators on average. On May 26, 2013, that was over 7 years ago, the mean age of 30 randomly selected Republican senators was 61 years, 247 days old, with a standard deviation of 10.17 years. The mean age of 30 randomly selected Democratic senators was 61 years, 257 days old, with a standard deviation of 9.55. Okay, from reading that paragraph, it looks like the ages are about the same, right? At least based on this evidence, based on this sample, the mean ages are only about 10 days apart. '61 and 247 for Republicans versus 61 and 257 for Democrats. All right. Here's the question. Do the data indicate that Democratic senators are older than Republican senators on average? Test at the 5% level of significance. Okay. All right. So the test will claim is that Democratic senators are older. Okay. So let's denote mu1 as the population mean of Democratic senators. The other population is the Republican ages, and we'll call that mean mu2. Our claim is that Democratic senators are older, so we want to test the claim here in the alternative that mu1, remember the first population are the Democrats, so mu1 minus mu2 is positive, so it's a right tail test. Okay, so we can use the T or the Z. We'll use the Z in this case. We're right on the margin, right on the cut line there of 30. We'll use the Z test here. That's our choice. And in StatCrunch, we get the following results. Notice the difference in means is 10 days, right? And what percentage of 10 days is a year? Let's figure that out. Okay. It's about 0.29. 0.029, very, very small difference. Look at the p-value of this test, or look at the z-stat. Z-stat is very small, it's about 0.01, and the p-value is very large. If the p-value is high, the null hypothesis will fly. We will not reject the null. Okay? And we'll conclude that based on the evidence at the 5% level of significance, we do not reject. So there is not sufficient evidence to conclude that Democratic senators are older. And we sort of knew that going in, didn't we? There's a very, very small difference in age here in the two samples. So even going through the analysis, we were probably going to reject the null. Okay? All right. Excuse me. We were not going to reject the null. We were going to accept the null because the p-value is high. So we can't conclude, we cannot conclude based on this sample that the Democrats are older on the average. Any questions about this problem? There's no data here. All we have is the summary data. Okay, unlike number 3. Okay, let's do the last problem here. Researchers conducted a study of smartphone use among adults. A cell phone company claimed that iPhone smartphones are more popular with whites, non-Hispanic, than with African Americans. The results of the survey indicate that of the 232 African American cell phone owners randomly sampled, 5% have an iPhone. Of the 1,343 white cell phone owners randomly sampled, 10% own an iPhone. Test at the 5% level of significance. Is the proportion of white iPhone owners greater than the proportion of African American iPhone owners? Okay, so let's take all that information, put it into a claim, and this is not a test of a mean, is it? It's a test of a proportion. The test statistic or the test score will have a Z distribution. Okay, that's given to you from your textbook. So let's set up the test just as we did before. We'll let P1 be the proportion of successes, that is the proportion of iPhone users in the white population, and P2 will be the proportion of African American iPhone users. This is important to denote which population is considered your P1 population or your P2 population. Here's our set of hypotheses. The proportions are the same. Okay. Remember, in the null hypothesis, we always have equality. So the proportions are the same, which is equivalent to the difference in proportions is 0, against the alternative that the difference is greater than 0. That is, the proportion of white iPhone users is greater. So that's our hypothesis. Null and alternative. For the test of two proportions, we always use the z-test. Okay? And what do we use for the counts? Well, that's easy because 5% of 232 gives us 11.6. Okay. And 10% of 1,343 is 134.3. That comes right out of the statement of the problem. From the random sample of African American users, we see that there were 5%. 5% of 232 is 11.6. 10% of 1343 is 134.3. Okay. And the sample difference is 5 percentage points. Okay. The z-stat is 2.42, 2.43 approximately. And the p-value is 0.0076. Okay. And we see here that comparing the p-value with the significance level of 5%, it's much smaller than 5%. So when the p-value is low, H0 is a no-go. We reject H0. Okay. Similarly, we can find the critical value for this right tail test, compare the z-stat, and the z-stat here of 2.43 is greater than 1.645, we reject H0. So the conclusion is the following. At the 5% significance level, there is sufficient evidence to conclude that the proportion of white iPhone users is greater than the proportion of African American iPhone users. Okay. Again, test of proportions requires the Z statistic. Fill in your StatCrunch two sample proportions test. And then based on those results of the test, make your decision. Okay, we've covered a lot of ground here. And I hope that most of this, if not all of it, made sense for you. It's important to look at these videos because we didn't do this in StatCrunch, did we? So you're going to have to go into StatCrunch and look at your videos here and then populate your spreadsheets with the data and you're off and running. Okay. Okay, let me just check our chats here. Okay, Noah, are you okay with your question here?
Hello?
Yes.
Hi, so on my, this is like completely off topic, like it's not related to what we just learned, but on my lab, there's like review quizzes. I remember at the first or second week, you said those were optional and we didn't have to do them, and I just wanted to confirm that those were optional.
That's correct.
Okay, so like those won't be factored into our grade at all or anything, right?
They will not be factored in, no.
Okay, and then there's like review homework for those quizzes. We don't have to do those either, right?
No, you just have to do the assignments.
Okay, okay, because like under the assignments page, there's like skills reviews, but I like they fall like under the same category, and I just wanted like to make sure those we didn't have to do those.
That's correct. Your grade will only be based on the actual homework assignments there.
Okay, sounds good. Okay.
Okay, and I see that there's some chat going on amongst the students there. Are there any questions?
did have one question about number 5. Towards the bottom of it, it mentioned a z sub c value. How did it find that?
Okay, z sub c is the notation that your textbook uses for critical values. Okay, those are the values that determine the rejection region, right?
Okay.
All right, now, let's see. So we're going to go to the Z calculator. And for a right tail test, we'll determine the value on this Z scale, which gives you exactly 5% probability. All right, so we'll switch this. We'll put an 0.5 here. And that shaded region there is the critical value Z sub C.
Gotcha. Okay, that makes sense. Thank you.
Let me just show you one other bit here. If it's a two-tail test at 5%, okay, then what is our critical value? Excuse me. I always do this, I'm sorry. This should be 0.95. Between doesn't give us the tails, it gives us the between. So 1 minus alpha is 95%, and now we get the correct critical values there. About -2 out to +2. See that?
Yeah. Okay.
So those are critical values. You get those based on alpha.
Gotcha.
Okay, guys, we have an office hour today at 11:30. So if you have any questions or concerns, I'll be back at 11:30. All right, same channel. All right. If there aren't any more questions, I'll end the meeting here. Everybody good with chats? Okay.
Alrighty. Thank you.
Everybody
Bye.
good?
Thank you.
Okay, thanks, guys. See you next Tuesday, all right? Next
Alrighty.
Tuesday will be our next meeting.
Bye.